Welcome to this number theory primer. In this lecture, we'll learn about the least common multiple of two integers, and let us recall at least one fact that we will use. So we have earlier proven that suppose we have two relatively prime integers, and if let's say a divides the product of b and c, where c is some integer, then a divides c. I've stated it for only positive integers, but that's okay, you can generalize very easily. We will only need it for this case. Anyway, these are the problems for practice. And now let us get started. So suppose we have two integers, none of them are 0, a and b, and define s as all those positive integers which are multiples of both a and b. Right? We are just collecting the common multiples of a and b. Clearly, this is basically what I'm trying to say is that this is a non-empty set, first of all. Right? And since neither of a and b is 0, it is well defined. Right, so this is a non-empty subset of natural numbers, simply because a times b is an integer which is divisible both by a and b. So this is a non-empty subset. And the least common multiple of a and b is defined as the smallest element of s. Since s is a non-empty subset of natural numbers, it has a smallest element. So that is the definition of the least common multiple of two integers, none of which are 0. Very simple definition and true to the phraseology. It is indeed the least common multiple. All right. So let's see what is its relation with the greatest common divisor. So fix two natural numbers a and b, and let's say d is their greatest common divisor. So we can write a as d times r and b as d times s for some natural numbers r and s. So then we claim that LCM is d times r times s. So this is very simple. First of all, note that a and b both divide d times r times s, simply because d times r is a, so a divides this guy, and d times s is b, so b divides that guy. So drs is indeed a common multiple of a and b, and thus LCM is at most any common multiple, and hence in particular this. So we have that. And now let n be any common multiple, be such that a divides n and b divides n. We will show that n is at least DRS. So this will finish the proof, because then LCM would be at least DRS, as we would have shown that any common multiple is at least DRS. And again, very easy. So we have, since a divides n, we have n is equal to ak for some k. So this is equal to drk, because a is equal to d times r. And now since b divides n, we have b divides drk, because n is equal to drk. This means ds divides drk, which means s divides rk. But now the GCD of r and s is 1. R and s are relatively prime, simply because we have already extracted out the greatest common divisor of a and b, so the two things must be relatively prime. So this implies s divides k, as we recalled in the beginning. Now since s divides k, k is equal to s times l for some positive integer l, and thus n is equal to drsl, and hence it is at least drs, and that's it. That is what we wanted to show. A very simple proof. And now let us finish the lecture with this observation, that GCD times LCM is the product of two integers. Again, let's say a and b are natural numbers. In fact, you have to take them to be natural numbers. You can maybe mess around a little bit and say both are negative, both are positive, but let's say they are just natural numbers for simplicity. So very simple. A is equal to dr and b is equal to ds, where d is equal to GCD. So what is LCM? As we just saw, LCM is DRS, and thus LCM times GCD is D square RS, which is dr times ds, which is a times b, and that's it. So this is something that we learn in high school, but I don't think we really ever learn the proof proper. And that's it for this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.